Okay, so this video is going to be over Energy 1B, which is related to kinetic energy and potential energy. Just like usual, you're going to have a practice assignment and a quiz over this section. Okay, so in the last video we talked about, a loose definition of energy as the ability to do work. We also talked about work and power, the concept behind those two things, and how to do calculations with work and power. But now we're going to focus more on actual types of energy, specifically on mechanical energy. And just to recap, remember that the unit for energy is the joule. The symbol for energy is a capital E, and then we use subscripts to denote different types of energy. Okay, now the two types of energy we're going to focus on today. This is a list of just some of the more common types of energy that you might see in this unit. But the two types of energy we're going to focus on today are kinetic energy and gravitational potential energy. Okay, so let's read what it says in the notes. Kinetic energy, it says, is the energy of motion. Okay, so kinetic means having to do with movement or motion. Okay, so it's very simple. If an object is moving, it has kinetic energy. If it's not moving, it doesn't have kinetic energy. Okay, the more motion it has, the more kinetic energy it has. Okay, if it's at rest or if it stops moving, it has no more kinetic energy. Okay, the symbol for kinetic energy that we're going to use is going to be EK. Okay, for kinetic energy. Now the second type of energy we're going to focus on is gravitational potential energy. Okay, now potential energy is basically energy that you can store and that you have the potential to use later on. Gravitational potential energy is a special type of potential energy whereby the energy is stored because of an object's height above the ground. Okay, so gravitational potential energy has to do with height. Now there's other types of potential energy you can have. For example, there's something called spring potential energy. If you've ever shot a rubber band, or if you've ever used like a mouse trap or a rat trap, when you pull the spring back and you lock it, you're storing energy in the spring. Okay, so there's different types of potential energy, but we're going to focus on gravitational potential energy, which has to do with height above the ground. Okay, so for example, if you take something, if you lift it off of the ground and you drop it, when you lift it off of the ground, you're storing energy in the form of gravitational potential energy that can be used up whenever it starts to fall. So as you lift something up and then you drop it, as it falls down, it loses height. Okay, that means it loses potential energy, but gains maybe like kinetic energy. Okay, so maybe it falls faster and faster. So we'll talk more about that a little bit later. The symbol we're going to use for gravitational potential energy is going to be EG. And now you're not going to see this in too many problems right now, but there's also thermal energy, or what you call heat, which you typically see when you have problems involving friction. Okay, so we're not going to see a ton of problems involving friction, but just know in situations where you do have friction, the energy it produces is heat. Okay, so that's why, for example, if you're driving along, if you slam on your brakes, friction makes your car stop moving, but your tires get really hot because of all that thermal energy, because of that heat. And that's why if you stop fast enough, you can actually smell the rubber in your tires burning. Okay, and of course we've talked about work, which is not a type of energy, but work is the transfer of energy to or from an object. Now in the last video we also talked about the conservation of energy, which is basically the key principle in physics that says that all energy in a situation cannot be created or destroyed. It stays constant, but it can change from one form to another. So let me show you a simulation really quickly so you understand what I mean. Pause it here if you need to get any of this down. Okay, so let's take a look at a quick simulation. So here we have a skater, and the skater is on a ramp. As you can see, she's going back and forth, and I'm going to make it so there's no friction. Okay, now what I want you to see is I want you to see what's happening to her energy as she skates back and forth. Okay, now let me go in slow motion. Now the blue on the graphs is representative of the gravitational potential energy of the girl. Okay, remember gravitational potential energy, that's that EG, that has to do with her height above the ground. And the green represents the kinetic energy, her energy of motion. Okay, so watch this. Actually, let me reset this. Okay, so in slow motion, as she goes down, notice that she is losing height. And because she's losing height, okay, she's losing that gravitational potential energy. But that energy can't just go away, right? Because energy is conserved, stays constant. What happens is it changes form. So as she goes down, she loses that potential energy, but she gains the same amount of kinetic energy. Okay, and you can see that at the very bottom, now she has no more height. All of that gravitational potential energy has been changed into kinetic energy. Okay, that means she has the most motion at the bottom. Now if she keeps going, okay, as she goes up, she's going to slow down, and at her maximum height, at her highest point, she's going to stop moving. Okay, we've talked about that before. Okay, because she stops moving at the highest point, notice her kinetic energy has gone back down to 0. But that kinetic energy was not destroyed, it was just transformed into gravitational potential energy. So if there's no friction, we're just going to keep having this back and forth where there's this constant exchange between potential energy and kinetic energy. Okay, and you can see that I'll speed it up like so. Now, if I were to add friction, of course she would slow down and eventually stop, and that would cause there to be heat, thermal energy. So let me add a little bit of friction and you can see what happens. Okay, so now notice the pie chart hasn't changed in size. It's the same amount of energy. It's just now all starting to become thermal energy. Okay, and so she's going to move slower and slower. She's not going to go up as high. Okay, now she's starting to slow down, and eventually she's going to come to a stop. Okay, and you'll see that momentarily. Okay, but notice the amount of energy that she started with is still the same. It's just now all of it has become thermal energy. Okay, so that's the idea behind, kinetic energy and potential energy and the conservation of energy, that back and forth exchange where energy can't, increase or decrease, but it can change forms. Okay, so let's talk calculations. Now there is an equation for kinetic energy. Remember, kinetic energy is the energy of motion, and the equation for kinetic energy looks like this. We have EK for kinetic energy equals 1/2 times m, where m is the mass of the object. Remember, mass is measured in kilograms. Okay, times v squared, where v is the speed, or if you prefer, the velocity of the object, how fast it's moving. Okay, so that is the equation for kinetic energy. Okay, 1/2 mv squared. By the way, before anyone asks me, the only thing being squared is the v. So it's 1/2 times the mass times v squared. Okay, so it's not the whole thing that's squared, it's only the speed. Now, the unit for kinetic energy, just like any type of energy, the unit for energy is always the joule. That's where we write the capital J for joule. And it says what factor influences kinetic energy the most. Now, there's two things in the equation, mass and speed. Okay, now they're both important, but if you look in the equation, notice the speed is being squared. Okay, so v squared is basically v times v. So even though mass is important, it's almost like the speed counts double, because it's v times v again. Okay, so the factor that influences kinetic energy the most is speed. Okay, that's that v in the equation, because it's being squared. Notice that if the speed was 0, 0 squared is 0, and this whole equation would equal 0. Okay, so if an object is not moving, it has no kinetic energy. Pause it there if you need to add that to your notes. Okay, let's do some quick calculation examples. Example 1. It says a 4 kilogram toy car. As you go through, make sure you identify your given information. 4 kilograms. Kilogram is the unit for mass. Okay, so that's my m. Travels along a tabletop. Calculate the kinetic energy if the speed of the car is 2 meters per second and 4 meters per second. Okay, so if the speed is 2 meters per second, we would have 1/2 times 4 times 2 squared. Remember your order of operations, you should do the exponent first. So 2 squared is 4. 4 times 4 is 16. And then half of 16 is 8 joules. Okay, now let's do the calculation when it's 4 meters per second. So in other words, let's see what happens if we double the speed. Now you might think if we double the speed, if we go from 2 to 4, that we double the kinetic energy, but that's actually not what happens. Watch this. Okay, so now I'm going to plug in, my mass is the same, but now I'm going to plug in for V, I'm going to put 4 squared. And let's do this again. 4 squared is 16. 16 times 4 is 64. And then half of that is 32. Okay, and so when we double the speed from 2 meters per second to 4 meters per second, notice we actually increase the energy by a factor of 4. Okay, so that's why I said on the last slide that speed is much more important than mass in the kinetic energy equation. All right, now take a look at the second example. We have the mass of a motorcycle, and we're given the kinetic energy is 12,000 joules. So we're given EK. Calculate how fast. How fast is always going to be a question about speed or velocity. So V is my unknown. That's what I'm trying to find. I choose my kinetic energy equation. I'm going to plug in, and then I'm just going to simplify and solve. I have 1/2 times 600 times V squared. Okay, now I am going to have to square root the V in just a second, but before I do that, let me clean this up a little bit. Okay, because I can actually combine the 1/2 and the 600. Half of 600 is just 300. Okay, and remember when you solve for something using algebra, you always want to do PEMDAS backwards. Okay, so the first thing we're going to do is not the square root. We're actually going to divide both sides by 300 because we want to take care of that 300 before we take care of the square root. Okay, so I'm going to do 12,000 divided by 300. Okay, and then I'm going to take the square root of that. Okay, so 12,000 divided by 300 is 40. And when I take the square root of 40, I get 6. Sorry, 12,000 divided by 300 is 40. And so my last step then is going to be to take the square root on both sides, and I get V equals 6.32 meters per second. Okay, usually in a problem it tells you how many decimal places to round to. Okay, so simple calculations involving the kinetic energy equation. Please pause it there if you need to look at those examples. Okay, the calculations we'll be doing in this video are pretty simple. The next video they'll get more challenging. So let's go on. Okay, the other type of energy we're going to talk about is gravitational potential energy. And remember, gravitational potential energy is energy stored due to height above the ground. Okay, now the equation for gravitational potential energy looks like this. Eg, that's the gravitational potential energy, equals m times g times h. Okay, where g, we are going to use a positive 10 meters per second squared. Now, some of you might be asking, why are we using a positive 10 and not a negative 10? Because when it comes to energy, the negative sign doesn't matter because the direction does not matter for energy. Okay, that's why we're using a positive 10 and not a negative 10. In the first semester, we used negative 10 for the acceleration due to gravity because the direction was important then, and now it's not. Okay, so that's why we're using a positive 10. So we have the mass of the object times g, which is a constant, that's the acceleration due to gravity. On Earth, the value is close to 10 meters per second squared, times h, where h is the height above the ground. Okay, mgh, very simple equation. The unit is the joule, just like it is for any type of energy. What factors influence it? Well, obviously mass, and obviously height. Okay, because you can see m and h in the equation. G, remember, is a constant as long as you're on the planet Earth. It's the same value. Okay, so pause it there if you need to add that to your notes. And we're just going to do a quick couple examples with this equation. Example 5, we have a 65 kilogram girl. So we have the mass of the girl given to us. Sits at the top of the slide, which is 2.4 meters high off of the ground. So here we're given h, which is the height. We're asked to find the gravitational potential energy of the girl at the top of the slide, halfway down the slide, and at the bottom of the slide. So I'm going to try to draw a slide. I don't know if I can. Okay, so something like this. Okay, so imagine there's a girl, and here's a slide. Again, It's hard for me to draw even under the best of circumstances, much less on a computer. But here's a girl, and the slide is 2.4 meters high. Okay, so that's how high she is off the ground at the top of the slide. So if I want to find the gravitational potential energy at the top of the slide, I'm going to use mgh, right? Because that's the equation for gravitational potential is mgh. And I'm going to do 65 times 10 times the height, which is 2.4. Okay, and so 65 times 10 times 2.4 equals 1,560 joules. Now, as she slides down the slide, she loses height. That means she loses gravitational potential energy. Okay, so halfway down the slide, when she's at the halfway point, right here, her height is half as much. So I'm going to do mgh, but now the height is going to be what? It's going to be half of the 2.4, which is 1.2. Okay, and so now her gravitational potential energy is 780 joules. And at the bottom of the slide, what is her height at the bottom of the slide? Well, at the bottom of the slide, she has no more height. Her height is 0. Okay, so her EG would be 0. Now remember that energy is going down, but her total energy is not disappearing. It's just being transformed. So as EG gets smaller and smaller, where is that energy going? It's going into kinetic energy. Okay, so she slides faster and faster and faster as she goes down the slide. Okay, so that is example 5. Pause it there if you need to look at those calculations. And let's do one more quick example. Okay, example 6. Okay, so we have a little monkey sitting in a tree. We have the mass of the monkey. It's a 14-kilogram monkey. And we're told that the monkey possesses 2,800 joules of gravitational potential energy. Okay, so here we have EG. And we're told to calculate the height now. So that's our unknown of the tree. Okay, so we have our equation for gravitational potential energy. I take my equation, I plug in my given. EG is 2,800. The mass of the monkey is 14. Remember G, that's a positive 10. That's the acceleration due to gravity. That's the constant. And then H is the unknown. Okay, and now I'm going to simplify a little bit before I use algebra to solve. 14 times 10 is 140. I say, okay, what's being done to H? It's being multiplied by 140. So to undo that multiplication, I want to divide both sides by 140. Okay, if I do it on one side, I have to do it on the other. And so I find that the height is 2,800 divided by 140, which is 20 meters, which is a pretty tall tree. Okay, if you want to know what a meter is somewhere around 3 feet. It's not exactly 3 feet, but it's pretty close to 3 feet. Okay, so that is example 6. Okay, so in this video we did very basic calculations with kinetic energy and gravitational potential energy. We talked about the difference between those two and a little bit about the idea of the conservation of energy. Okay, now in the next video we will spend more time talking about this conservation of energy thing and doing calculations with conservation of energy. Okay, so for now just work on your practice problems and your quiz involving these basic energy calculations. Please let me know if you have any questions, and as always I will see you guys in the next video.